Okay, let's talk about writing and balancing chemical equations. So first, when you write and balance a chemical equation, you need to realize that mass must be conserved. Okay, so initially when you write out the chemical equation, you're concerned with what substances you have. And so initially when you write those chemical formulas of the reactants and the products, it may not actually be what we call balanced, okay? And so it may not initially appear that mass is conserved, but once you know what you have, you need to balance the reaction. So you need to make sure that there's the same number of atoms of each element on the reactant side and the product side of a reaction, okay? Because we're not talking about nuclear reactions. So you're not going to have a conversion from one element to another. Okay, so the elements that you start with must be there in the end as well. And you have to have the same number of atoms of each. Okay, and that would then make the mass conserved. Okay, you would have the same number of atoms of each element on each side of the reaction. Now, when you're dealing with a chemical equation, you actually have two different types of numbers that will be in the equation. And so let's talk about these two because they serve two completely different purposes, but both contribute to conserving the mass in the reaction, essentially. Um, so first, you have subscripts, okay? And you need to be careful because the subscripts they don't carry from the reactants to the products. Okay. Now, occasionally there'll be an element that's on the left side and it has a particular subscript, and on the right side of the reaction, it may have that same subscript. But a lot of times that is not true. Okay. It definitely does not have to be true. Um, and so these subscripts are actually specific to what substance you have. Okay. And they're things that you should not change when you're trying to balance the reaction. Okay, so the subscripts you place initially as you're writing the chemical formulas of the compounds. Okay, so let's say you have water in the reaction, then the formula for water is H2O. It's always H2O. It doesn't matter if you need more hydrogens on one side or less hydrogens. Okay, you have to write it as H2O because that is the chemical compound, okay? And when you go through and start doing the actual balancing, making sure mass is conserved on each side, you won't go through and change subscripts, you won't add subscripts, okay? If you do, you're changing what substance you have. So the subscripts are something that are going to come with what you have. That's what you're going to be writing down first when you write down um, your formulas for each compound. But once you have all of that written down, that's when you start actually balancing the reaction. And when you start balancing the reaction, what you do is you add coefficients. Okay. And the coefficients are actually to make sure that the mass is balanced on each side, or to make sure that there's the same number of atoms of each element on each side of the reaction. Okay, and so these coefficients go in front of the chemical formulas. Okay, whereas the subscripts are inside the formula, right? It's a subscript next to the letter that it applies to, or the chemical symbol that it applies to. The coefficients get added onto the front of a chemical formula. And that coefficient then applies to everything in that formula. So let's say we have a water molecule in our reaction. If you put a 2 in front of that, so 2 and then H2O, that means you actually have 2 H2O molecules, or in total 4 hydrogens and 2 oxygens. So that coefficient applies to everything in that formula. Now, when you're doing your balancing, if you only need one of something, you don't usually put a 1 in front of the substance. We just leave that off. So if there's not a coefficient in front of something, then it means that you have one of those things. And in the end, when you add coefficients to things on the reactant side and product side to balance and you make sure all the atoms are equal, or the atoms of each element are equal on the reactant side and product side, then you need to make sure that your coefficients are the lowest whole number ratio possible. Okay. So sometimes when you go through and do the balancing, sometimes people accidentally, scale things up a little too much. And so they maybe double something when they didn't really need to. And so then the coefficients are higher numbers than they need to be. And so they could be scaled down. Say everything could be divided by 2 or something like that. Also, sometimes when people balance, some people like to start off balancing with fractions. It can be useful sometimes. At first, that can be confusing. But if you do start off balancing with fractions, then at the end you have to make sure they're whole numbers. Okay, the coefficients should be whole numbers. Every once in a great while, we will look at reactions with fractional coefficients. But if you're asked to balance a reaction, it should have whole numbers. It should be the lowest possible whole numbers. Okay. Now, a couple of hints for balancing reactions. It's generally best to begin with trying to balance an element that's only in one reactant and one product. Okay, so occasionally you'll have a chemical reaction where there's an element that's in every single thing in the reaction. Okay, this happens a lot with like oxygen. And so don't start with that. If you do, then when you change one substance and then you change another, both of those things are changing that element. And it can get really confusing and be very tricky to balance if you're focused on something that is more complicated. Another thing, if you have polyatomic ions in these substances, it can be helpful to treat them as if they were one element. Okay, so like if you have a PO4, meaning a phosphate on the reactant side, and you have a PO4 on the product side, then you can treat the PO4 as one thing and just count how many PO4s you have instead of counting the phosphorus and the oxygen separate. Okay, so sometimes that's useful. Another thing is a lot of times oxygen and hydrogen tend to be more complicated. They tend to be in more substances. So a lot of times I'd say try to save them to last, because sometimes as you balance all the other elements, it'll fix, oxygen and hydrogen, or kind of force you to do it right. And so there's not one set of rules that will definitely tell you how to balance a chemical equation. For the most part, it is trial and error. Okay, and so you can start with any element in the reaction, balance that by adding coefficients, and then go to the next element and so on. Okay, but you can start anywhere you want. You just kind of, sometimes as you change one thing, it messes something else up. So you may have to go back and rebalance. So it's more of trial and error and kind of experience. As you balance more equations, you get better at it. But just keep in mind, try to start with simple things. Okay, so let's look at some equations. We're going to try to balance some. Okay, so I've given you here 4 different reactions. None of them are balanced. Okay, and I say to balance these equations. Okay, so what we need to do is we need to add coefficients. So notice that all of these reactions have subscripts in them. Those subscripts are part of the compound. So Au2S3, the reason there's a 2 with the Au and a 3 with the S is because that's an ionic compound made up of gold 3 ion and sulfide ion, and they have to combine in a ratio of 2:3 to make it neutral. Okay, and so those subscripts are part of that compound. If you changed them, it would be a different substance. So you can't do that. Okay, so we need to add coefficients, or sometimes we call those stoichiometric coefficients, and that's because we use them to do what we call stoichiometry, which are calculations associated with reactions. Okay, which we will talk about in another video. But for now, let's balance these. And so you can start wherever you want. You just need to pick an element on the left side, look at how many atoms there are, look at that same element on the right side, and look at how many atoms there are. And then you're going to add a coefficient to fix any difference. Okay, so let's just start with gold. And so gold on the left-hand side, we have got 2 atoms, and on the right, we only have 1, right? And so if we put a 2 in front of the AU, now we have 2 gold atoms on the right as well. Okay, you can't add a subscript because that would say that you're bonding one gold atom to another, and that would be a totally different substance, which doesn't actually exist. So we won't do that. We add a coefficient. Okay, now next one, let's see here. We've got sulfur. There's 3 of those on one side, and there's only 1 on the other. So I can put a 3 in front. Okay. And then last, I've got hydrogen. I've got 2 on the left. And on the right, there's 2 in H2S, but I have 3 of those H2S molecules. So in total, I have 6 of those right now. Okay. And so if I put a 3 in front of the H2, then that's going to also give me 6 hydrogens. Okay. And so that would be our balanced reaction. Is we don't put a coefficient on the Au2S3, having, just one of those is sufficient. And then we have a 3 in front of the H2, a 2 in front of the Au, and a 3 in front of the H2S. And so that is our balanced reaction. Now, the next one, this has got a lot more stuff going on. So the first one, we only had 3 elements. This next one, we've got calcium, we've got nitrogen, we've got oxygen, we've got aluminum, we've got phosphorus. So we've got 5 different things. It's starting to get complicated. And you notice that oxygen is in everything in that reaction. So you definitely don't want to start by trying to count oxygens, okay? But another thing that it would be helpful to notice here is looking at the polyatomic ions. So on the left side, we've got NO2, so the nitrite ion, and on the right side, we also have that NO2. And then on the left side, we have PO3, that's the phosphide ion, and on the right, we have the PO3, okay? So we can treat those as just if they were one atom, okay? And that'll make things a little bit quicker, okay? And you can start wherever you want. I'm just going to start at the left, I guess. So we have calcium, we have 1 of those, and then I have 3 calciums on the right side. So I'm going to put a 3 in front of that CaNO2, okay? And so that'll balance my calcium. And then let's just go ahead and look at the NO2 part. So the NO2, there's 2 of those in the calcium nitrite, right? And if we have 3 calcium nitrites, then we have a total of 6 of those NO2s on the left, okay? And then on the right, there's 3 of them in the aluminum nitrite compound, okay? So if I make 2 of these aluminum nitrites, then that would give me 6 of those nitrites. I have a 2 in front of there. Okay. Then next, if we look at our aluminum, there's 1 on the left-hand side. And right now, because I made 2 of the aluminum nitrites, I have 2 aluminums on the right. So I'm going to put a 2 in front of the aluminum phosphite. And then the last thing, I can look at those phosphites. There's 1 in the compound, and so 1 of those, and there's 2 of the compound, so there's 2 phosphites, and there are 2 phosphites already on the right-hand side. So I should be done with my balancing. You could go through and count the elements individually. So instead of counting the NO2s as one thing, you can count the nitrogens separate from those oxygens. And you should come up with the same balancing. It's just a little bit easier if you notice that that stayed the same, on both sides. And so you can actually just count them together. And so that's what I would do. And so this would be your balancing. is with the coefficients of 3, 2, 1, and 2. And keep in mind, we don't actually write a 1 in front of the calcium phosphite. But if you wanted to write a number, it would be a 1. Okay, next one. Again, this one's pretty complicated. We've got nitrogen, hydrogen, phosphorus, oxygen, tin, and chlorine. So now we've got 6 different things going on. So you can count individual elements. I wouldn't start there. I would treat things as clusters, so as their polyatomic ions. So here we have NH4, which is the ammonium ion. Okay, I have 3 on the left, so I'm going to go ahead and put a 3 in front, so I have 3 on the right. Okay, and then I have phosphate on the left and phosphate on the right. I've got 4 on the right and only 1 on the left. So I'm going to put a 4 in front of that to make 4 phosphates. But if I do that, now I messed up what I started with. Okay, and sometimes that happens. And so now I actually have 3 in the compound of the ammonium, and then there's 4 of the compound. So there's actually 12 now. Okay, and so I need to go and change that initial coefficient that I wrote and change it to 12 instead. Okay, so sometimes that happens. You got to go back and fix things. Now then, if we look at, we've got 10, there's only 1 on the left and there's 3 on the right. So I'm going to put a 3 in front of that compound. And then the ClO3, or the chlorate ion, I've got 4 in that compound. And if I have 3 of that, then that means that I have 12 of those. Okay. And I have 12 of those on the right. Okay. So that should be my balanced equation. Again, you can go through and count those things individually, the individual atoms, but when you have those polyatomic ions, it's much easier to focus on them as a whole, and count them as one piece on the left and the right, and it works the same. Okay, last one, we've got H2SO4 and PbOH4. And so that you've got what? Hydrogen, sulfur, oxygen, lead. And so you've got 4 different things. You could go through and count them individually, but some of this will kind of treat together. And so there is oxygen in everything. There's hydrogen in 3 of the 4 substances. And so I would start by looking at, say, like lead. Well, the lead, there's 1 on each side. Okay. Next thing I would look at is, well, you have a polyatomic that's on both sides, specifically the sulfate is on both sides, and you have 1 on one side and 2 on the other, right? We have 2 on the product side and only 1 on the reactant, so we definitely need 2 of the H2SO4s, okay? And so now the sulfate and the lead are balanced, but then we're down to hydrogen and then this OH. And OH you can't clearly see on the right side. And so then you can either, count up your hydrogens or count up your oxygens to figure out how you balance what remains. Or what's usually helpful is if you realize in this reaction, what's really happening is that H2O is formed by the combination of H plus and OH minus. And the OH minus comes from that PbOH4. And so if there's 4 of those, then you must form 4 waters, okay? And so that should actually balance the reaction. And so you can go back and check by counting up all the hydrogens, counting up all the oxygens. I'll just count up at least the hydrogens here. If we count up the hydrogens, you've got what, 4 hydrogens here. You've got 4 hydrogens here. And then we've got 8 from the water. So we do have 8 on the left and 8 on the right. So the hydrogen's balanced. You can check also, oops, I need my 4 to stay there. You can check oxygen as well. And so the oxygen, you've got 8 here because 2 of the SO4s. And then you've got 4 here. And you've got 8. And you've got 4. So we've got 12 on each side. So the oxygen's balanced. And the lead, there's 1 on each side. The sulfur, there's 2 on each side. And so that is balanced. Okay, so that one's probably out of all of them the trickiest one, because a lot of people don't realize that water molecule, it actually came from H plus and OH minus. So that can help you balance this a little quicker than counting the individual elements. But as I said, balancing reactions, there's not a definite method that will always work for every single one. So a certain steps that you need to follow. It's more trial and error. You've got to go back and forth and just make sure you have the same number of atoms of each element. Now let's do one more task. So we're going to write some balanced chemical equations. Sorry, based on the words that tell us about the reaction. Okay, so I've given you a statement telling you about some different reactions, and I want the balanced chemical equations. So we're just going to go through these and write them out and then balance them. So you always have to write the reaction first. You have to identify what are the reactants, what are the products. Once you have all of that stuff, then you can add coefficients. So that's what we're going to be doing. So first I say oxygen gas reacts with solid copper metal to form solid copper 2 oxide. Okay. So I start off by telling you oxygen gas reacts with solid copper. So oxygen gas is a reactant, solid copper metal is the other one. So you need to know oxygen gas is one of our diatomic elements. Okay, so it's O2, not just O. Okay, and it's a gas, so we'll put in parentheses the G. And then it reacts with solid copper metal. Now, all metals exist as atomic elements, and so it would just be Cu, and it's a solid. And then I say that it forms solid copper 2 oxide. Okay, so we're going to form solid copper 2 oxide. So copper 2 is Cu2 plus, and then the oxide part's O2 minus. So those combine in a 1-to-1 ratio. So the formula of that is CuO, and it is a solid. Okay, so that's the information that you get directly from the explanation of what reaction is occurring. Okay, but then it needs to be balanced. So if you look at this, you've got 2 oxygens on the left and only 1 on the right. So we would need to have 2 of these copper 2 oxide units form. And then right now we have 1 copper on the left and 2 coppers on the right. So I'm going to have to put a 2 also in front of the copper. Okay, so that would be my balanced chemical equation for that particular reaction. Now, the next one, we've got magnesium metal, and that reacts with hydrochloric acid. Okay, so those are our reactants. And so magnesium, since it's a metal, it's Mg, no subscript, because metals just exist as individual atoms. And since it's a metal, it's a solid. If it weren't a solid, we would say like molten metal, meaning it's liquid. And so metals you should always assume are solid, unless if you're told otherwise. Then that reacts with hydrochloric acid. And you have to know what hydrochloric acid is. So the hydro and the ic part help you with that. That means it came from chloride, okay, or it releases chloride ion, really. So Cl minus. So whatever that is when it's combined with H plus. So Cl minus combined with H plus is HCl, okay? And so hydrochloric acid is HCl aqueous, okay? When we use that term acid, it's always an aqueous solution, okay? So every acid should have a phase of AQ, okay? And then we say it forms aqueous magnesium chloride, okay? So magnesium chloride, that's an ionic compound because it's a metal and a non-metal. And so you need to be able to figure out the chemical formula of that. And so that's made up of Mg2 plus and Cl minus. And so those need to combine in a 1:2 ratio. You need 2 chlorides for every 1 magnesium. So that would be MgCl2 would be the formula for that. And then we have, oh, and that was aqueous. So I'll put aqueous next to it. And then it says, and hydrogen gas. And hydrogen is one of our diatomics. So it would be H2 gas, not just H. So you do need to know how different elements exist by themselves. So you need to know all metals are just one atom and they're in the solid phase, unless if it's mercury, then it's liquid. And you need to know the 7 diatomics. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay. And so that is the substances that are reacting and being formed, but then we need to make sure it's balanced. Well, right now I have 1 magnesium on the left, 1 magnesium on the right. I have 1 hydrogen on the left, 2 hydrogens on the right. So I'm going to put a 2 in front of HCl. And then I have 2 Cl's on the left and 2 Cl's on the right. So that's balanced. And then the next one, I have hydrogen gas and iron 3 oxide powder react to form liquid water and solid iron powder. So the first things given are the reactants. So hydrogen gas, so that again is H2, G in parentheses. And then iron 3 oxide. So you need to know iron 3 oxide, that's made up of Fe3 plus, so iron 3 ion, and oxide ion, which is O2 minus. And so those are going to combine in a 2:3 ratio to make it neutral. So that would be Fe2O3. And we say that's a powder, so that means that's a solid. Okay, these powders are solids. And then next up, we say it reacts to form liquid water, so H2O liquid, and solid iron powder. So Fe is iron, and it's a solid. Okay, so that's the substances reacting and being formed. Now I need to make sure it's balanced. Okay, so to start with, let's see, we have 2 hydrogens on the left, 2 hydrogens on the right. And then I have 2 irons on the left and only 1 on the right, so I could put a 2 in front of that. And then I have 3 oxygens on the left and only 1 on the right. Well, I could put a 3 in front of the H2O. But once I do that, you've got to be careful because I already counted my hydrogens. So if I put a 3 in front of the H2O, now I have 6 hydrogens on the right. So I need to make sure I have 6 on the left. So I'm going to put a 3 in front of the H2 to make that balanced. And so now I should have a balanced reaction. Okay, now last one, hydrogen gas and aqueous aluminum chloride are produced when solid aluminum is reacted with hydrochloric acid. Okay, now you have to be careful with this because it's telling you the products first, right? Hydrogen gas and aqueous aluminum chloride are produced. So those are the things on the right side, hydrogen gas, H2 gas, and then aluminum chloride. If we have aluminum chloride, that's an ionic compound that's made up of Al3 plus or aluminum ion, and then Cl minus, chloride ion. So those combine in a ratio to make it neutral. So it's going to be a 1:3 ratio. So AlCl3. Okay. And we said that's aqueous. So we label that as AQ. Okay. So those are our products. Now let's see. What are our reactants? Oops. Sorry. That's not supposed to happen. Go. Okay, so now let's see. I'll ignore this stuff. Don't let it distract you. Now it says they're produced when solid aluminum, so aluminum is a metal, it exists just as Al, and it's a solid. is reacted with hydrochloric acid. So we had just had hydrochloric acid above, so that's HCl, okay? And it's an acid, so it's aqueous. All acids are aqueous. And now we need to balance. So if we start at the left, we've got one aluminum, one aluminum. We got one hydrogen, two hydrogens, so we're going to put a 2 in front of the HCl. And now I have 2 chlorines on one side and 3 on the other. So that's not going to work. And so I have to think about 2 and 3. The lowest thing I can get to from both of them, or the lowest common multiple, is 6. So if I can get 6 chlorines on each side, then that is the best way I can do that. So that would be 6 HCl's instead, and 2 aluminum chlorides. But if I put a 6 in front of HCl instead of the 2, now I changed my hydrogens. So I have 6 hydrogens on the left, I need 6 on the right, so I'm going to have to put a 3 in front of the H2. Okay, and then also I added the 2 in front of AlCl3, so that changed my aluminum. So I'm going to have to go back and fix aluminum. So I have to put 2 in front of that. So you do have to be careful. Depending on where you start, you may have to go back and change things. And that's okay, but you just always need to make sure that you have everything balanced in the end.